pôr. Oh, Ana,
Ana, podes ir ali falar.
precisas de um browser, não é?
É. Não, põe no Google que é mais fácil.
Já chegaram.
Porque...
Tem bandeiras e tudo. Quero uma fotografia.
Não.
Onde é que esteja atento?
Em princípio eu tenho aqui, se não tiver.
Epá.
Tiver aqui, tem que abrir ainda.
Eu entro no canal, vamos fazer outra noção. Podes entrar no Google Drive, era isso que estava a dizer. Queres entrar no Google Drive?
Mas pode ser aí. Entras aí direto depois na tua coisa.
Se quiser abre uma sessão privada, que é para depois não guardar as credenciais.
Mas eu abro isto. Ou se calhar podes entrar diretamente nos slides.
Sim, sim.
Não há aqui. Não há aqui.
É aquela primeira ligação que toda a gente viu. Eu vou.
Vamos aguardar, sim, para atuar.
Olha, uma coisa também do Humberto diz assim: além de culpa do centro, porque o centro deles é muito bom como o nosso, ou seja, tu tens dinheiro em casa que não te dão aos filhos. Não, é caríssimo.
Mas acho que vale a pena. Aí vai ser chamado outra vez.
Também não precisa.
É que vocês estão a fazer aí desde isso. É que sabes porque é que eu faço no Google? Normalmente isto não tem problemas. E eu, com o telemóvel, posso fazer exatamente isto. Vocês estão a fazer a presentation.
Mas queres fazer com o telemóvel com isto?
Não, agora não posso fazer porque é por causa do sistema.
Vais ter que falar aqui também.
Tá, vou só pôr isto aqui porque tenho as notas aqui. Normalmente tenho as notas aqui, depois conecto aqui, depois ficam as notas aqui no telemóvel. Eu só clico no botão e as notas saem.
começa a botar a canela. Ela, os dois, nós mandamos para os manos.
Esse chapéu aqui.
Assim parece inteligente. Não vão apresentar?
Eu vou apresentar, mas ainda não está na hora, está bem?
Sim, sim, sim.
So good morning to everyone. We are in the last day of the conference, but it's the starting day to the session CAM, Computational and Mathematics and Applied Mathematics. Thank you to all to be here and online to be present in this session. So each presentation is about 15 minutes, okay? And the first speaker is Ana Leitão from the Faculty of Human Kinetics, University of Lisbon. She will talk about dynamics between order and chaos for family of two-dimensional cellular automata. Okay, Ana, please.
Hi everyone, thank you very much for inviting me. I'm quite nervous today because normally I work in another, go to other presentations, not the mathematics, so I feel like really stressed. But our work that we are presenting here with Ricardo, Professor Ricardo, is about this dynamic between order and chaos with the two-dimension cellular automata. And it started with the idea of dance. That's our area. So our main goal was to create this grid of Boolean cellular automata and to understand what was the dynamic that is inside of it, and to study the order between chaos and also order, and also to find out what was in the between, if there is a lot of configurations in the between that could be interesting for us in other areas, not just in the mathematical way, but also in the mathematical way. So here we can see, no, oops, sorry, eu acho que eu guardei ele. Como é que foi o comando? I'm sorry, I lost the command. Oh, here it is.
You are not allowed to steal anything from.
No, I'm not. I'm not going to steal anything. Okay.
Okay.
Now it works. Sorry. So for our starting point was to more or less figure out these dynamics and explore the special structures of fixed null boundary conditions, how it influences the structure, because we have a finite number of, if we see in a real world, we see a finite number. So it was our main idea to create a fixed boundary around. So the focus was to create this two-dimensional, because we could study as a plan, Boolean cellular automata, and put the fixed structure of null boundaries in-house and see how these conditions influence the emergence of the dynamic regimes beyond chaotic and order. And for that, we analyzed we tried to figure out the Wolfram ideas, the classification, and also to extend these ideas further. So, as we see, we have a finite number of grid, then parallel lattice Boolean cells with the von Neumann peripheral neighborhood that we see one cell on the top, on the sides, on the back. We don't consider the interior one, and it's also always updated synchronously every t moment, and we also have these zeros around to create like a frontier. So it's this kind of new, because mostly what has been studied was in the line, so we transferred it to the 2D dimension. And we also used the representation of the integer Wolfram studies, that we transformed the binary representation into an integer to make it easier to understand and also to simplify the calculations. So what is interesting when we see this is that this simple, like for example, here we have a 5-to-5 lattice Boolean cell with a random given configuration in the beginning. And we can see that there is like some patterns that come out. This is a really simple cellular Boolean lattice cellular automata, and we can see that the transient is really, it enters directly in the cycle really fast in the time of 7, and then we have a 8-time cycle that repeats here. So basically, it's interesting when we see the cellular automata, because they have these structures inside that we can see, because we are talking about this idea of chaos, that actually it's a deterministic chaos, so it has always a cycle. So it can be bigger, smaller, enter faster, go shorter, but it's always like it ends always in a cycle. So in this case, what we have, it's 65, more or less, thousand cellular automata, but it's really difficult to investigate this number of cellular automata, because we have a computer and it has some properties, and it's difficult to do all the investigation. So for that, we need to kind of reduce the number of cellular automata, and for that, we have used some of the dynamic equivalences that already Aguiar and Severino in 2015, they already have studied. And to adapted them to the fixed conditions of null boundary conditions. And what is interesting is that for that we cannot go further because the conjugacy symmetry cannot be used because also of these boundaries, because we cannot change from, in the boundary cannot change the zeros to 1 and the 1 to 0, so it's impossible to do that. So even though doing these dynamic equivalences and finding out these limitations, we figure out a number that is quite big, but it's small enough to study with the computer. That is this 9,000.7 more or less. And for that, after that, what we used was, okay, Hoffman said, okay, there is order, there is chaos, and there's something in between, and he had also classified them. Number class 1, class 2, class 3, class 4. So we said, so maybe we should start for doing that, classifying what is in the beginning and like not to see what is in the middle, but basically to say, okay, we need to exclude the ones that are not important for us in this, too ordered, it's not interesting, too chaotic, it's not interesting, so we need to exclude this. So what we have done was basically this. First, we studied the ones that go to the fix, point fix, that go directly, the dynamics goes directly to the fixed point fix, and there was a big, huge number, as we could see, and also it's in accordance to the idea that we have a lattice, so we make it shorter and compact, so it's normal that we arrive to a number of fixed points, that all the dynamics go to 0, all dynamics go to 1, and in this case, most of them go to 0, and one just go to the fixed point 1. And then there's the second class order, the second class that also goes to dynamics of order, that are shorter periods and shorter transients. They go really fast to the order. So with this, for that we have done, for example, 30 per 30 initial configuration in a lattice square that is big enough to say, okay, this number maybe has some chaos in it, so we need to see which of them are not chaotic at all and go directly to the system. And for that, we have done also 100 times steps that is really fast. We go directly. So if we seek for like 10,000 random configurations in the beginning to this cellular automata, we iterated. The ones that in the 100 times steps go directly to this transient short and short period would be also class 2. So we exclude all of them also. And this is also connected with the idea of boundaries, 0 boundaries around. So the system is really fast. But we can see that the summatory between the class 1 and class 2, it's really big. So it's 36% of the all huge number of cellular automata. And it's quite common because we are reducing the system, put it really small. So the next thing we have done is like, okay, so we have already the order, so we need to look for the unordered. And the idea was, they are constrained, really constrained cellular automata, and for sure there is some, but not too much. That was our intuition. But even though we have like a small, in this case, we have done the opposite. We have done a small cellular automatas, 8x8, and say like, if there is chaos in there, there will be chaos in the other, for sure. Because as it biggers, it increases the chaos. So we have done it 8x8 initial square, lattice square, and we have done 1,000 initial random configuration. And here what we have done is put a long time, but not too long enough to see that there is no entry in any cycle. So we have 1,000 time steps, and saw that in that cases there is no entering in the cycle, or so the transient is too big and we cannot see any pattern on it. So we figured out that there is 321 cellular automata that can be classified as class 3 under these conditions. And it's also expected because there is the limited boundary with 0, so it makes sense. It's a short number, but it's in accordance. So what is interesting is that when we do the sum of all, we can see that there is 7,000 more or less potential cellular automata that are in between of these configurations, and they are not chaotic, they are not ordered, and they are in the between. So when we studied it, we found, like, systematically, we found some configurations. One of them was this really interesting configuration that we see kind of a fluxus of a pattern that goes to the left, to the right, and we call it flow. It's really interesting because also in the areas you can see flow. When you run, when you dance, there is this, you enter in the flow. So this property is really, maybe there is something in here. So here we have a big system, 30 per 30, and there is a contradictory thing that happens, that we have a big attractor period, 28,000.7, and we have to enter in the cycle, we have a big transient. So it should be chaotic. It shouldn't be organized internally. But there is this property that we see visually, some kind of organization on it. And this is kind of counterintuitive, because inside of the boundaries, it shouldn't be, maybe you shouldn't see this flow, because what we have seen until now in Wolfram theory was, we see it when we don't have null boundaries. We have these periodic boundaries. So there is a circulation of the information. And here there is like a beginning and an ending. Also, okay, we see some divergence here in the end, but something that is a property from the cellular automata that emerges. It's like over the property of just numbers and bits changing. So this emergence effect is really interesting for us. So our main thought was like, okay, maybe this, and it's not just here, we have seen other examples with Professor Ricardo, we have seen other things, that maybe this idea of complexity that Wolfram brings is too tight. Because normally what Wolfram says is the opposite. It's like, okay, we have order, and sometimes some disorder happens. But here in this situation, we have the opposite. We have like a supposedly chaotic cellular automata, but visually we can see some property that emerge. And there is one guy in literature that is called Deleuze-Guattari, that he says the complexity has a dimension that is over, no? It's not the sum, of course, that we all know, but there is this something that appears over this emergent thing. So we think that it's really interesting to see this richness. For us, it's really interesting maybe there is more of this situations. So our main contribution is this idea that we need to study it more deeply, this cellular automata, even if it's really, really simple, because we have a really case of simple cellular automata. We have von Neumann interactions, and also we have the relation is just with 4, and it's a lattice square, it's in fixed null boundaries. It's not like a really complicated cellular automata. It's a really simple one. And even though we see some interesting structures, so we found out that maybe it's interesting to go back to these studies and see what is happening, not just having this idea that we have already studied everything, but maybe there is some properties that can be used and seen that are beyond what we have seen. So we have this idea with Ricardo, Professor Ricardo, that this says we need, of course, we need to do the mathematics on the behind and develop the quantitative criteria to sensitive spatial organization, propagation phenomena, and coexistence of flow, and so on. But we said, okay, maybe we need to use AI to check the patterns that come up over it and to see what can appear. Because actually this property of flow, and we hope to have something new in the next times, is it's something that in other areas a lot of people study. And as we can see here, is not the condition of the structure, but is really a property of the system. And with this, we finish. Thank you very much.
Thank you for this nice presentation. Are there any questions from the room or someone is online? Okay, only, okay, please.
Yeah, it would be necessary to use a supercomputer or something. You know, so many calculations and pictures, what you are using for producing this.
We just use the Mathematica, but we want to use also it's a normal computer. I think it's a little bit better, no, the one that we used, but it's not too much. Because we always shrinked the system, no? We already excluded a lot of very cellular automata, so it makes it. And one of the things it was interesting is that when we decided to use the video, then we could see, as I come from other areas also, sometimes we need to be more sensitive to the dynamics and not just the inert calculation. They are really simple, actually.
I did not know that one can study between order and chaos, something between. It's very amazing.
And I would like to do a question about it. Did you have already choose a name to this complexity between order and chaos? The name? No.
The word complexity is not supposed to be used. The idea is to have dynamics between order and chaos, and those that are closer to chaotic dynamics, those will be called complex, as Wolfram did. But in a certain sense, there is no word because they are very, very different. They are between chaos and order, but very different with each other. So there is no between.
Okay.
We think that maybe classification is not the best. It's good for studying these endings, but not inside.
Very stupid question. Is this Wolfram? Is the Wolfram from Wolfram research?
Yes.
Yes.
That's the same one. Okay. We are out of time. Let's thanks again to Anna. Thank you very much. We only choose. Change here. Next speaker, Isabel Cação from the University of Aveiro. Thank you for coming. Polynomials, structural properties, and zero bounds. Isabel, the floor is yours. Okay.
Thank you very much for the possibility of being here. So the work that I will present